We will continue with our discussions of potential flow. In our previous video, we talked about definition of a streamline, velocity potential, and also how they are related to each other, how they are one perpendicular to the other. We also showed that the combination of conservation of mass equation, which we call continuity equation, and the definition of irrotationality together leads to Laplace's equation for both for the velocity potential and also for stream function. We also discussed what we mean by irrotational flow, or also called potential flow in that context. Now we are going to look at some more concepts. So let's quickly review, starting with circulation. We have seen this before. So if you have a contour in space, closed contour in space, so some stream vortex lines are passing through it. So the bundle of vortex lines is sometimes called the vortex tube. So think of it as a vortex line, tubes are passing, lines are passing through it. You also have a flow velocity vectors crossing the boundary. I have drawn there so they are all parallel to each other, but they need not be. So this is a contour. So we break the contour into small line segments called delta S, starting point, ending point, x, x plus delta x, y, y plus delta y, z, z plus delta z. Therefore, delta S is simply delta x times I plus delta y times j plus delta z times k. Now the velocity vector is going to be in this direction along the streamline, tangent to the streamline as we saw earlier. So v dot ds is going to be a scalar product. So if you sum up the scalar product over all the small segments like this all around, that's called a contour integration. That's what we call circulation. According to Stokes' theorem, this circulation around the closed contour, I'm drawing it in the counterclockwise direction here. So if you look at there's vortex lines passing through it, entering this screen, for example, and coming out to the back end. So the vorticity is a vortex vector. We used to call it omega. Anderson calls it xi. If you dot with dA, where dA is an area vector, it's got an area magnitude. Its direction is normal to the contour. Okay, so the normal is now coming towards you. Okay. So xi dot dA, think of it again as a right-hand screw rule. So if the normal is coming towards you, you are rotating the screwdriver in the counterclockwise direction so that the screw advances towards you. Therefore, this is a en vector is perpendicular to the, in this case, plane of the paper at the centroid of the small element dA perpendicular to the paper in 2D. So xi dot dA is a scalar quantity. So if you sum up over all such dAs within this area, then that quantity should equal this line integral, which is circulation. So this is called the Stokes theorem. We will use it a little bit later, so we just park it. We need it, so we just remember to use it in the future. What does Stokes' theorem say? Basically, if you have a contour in the potential flow region, irrotational flow outside the boundary layer, since there's no vorticity there, remember it's an irrotational flow, then that means the vorticity vector is 0 because vorticity magnitude is 0. That means circulation is 0. Therefore, outside the boundary layer of a body, outside the wake of a body, if you take any closed contour, you're going to get 0 value for circulation. But the picture changes if you draw a contour integral surrounding the body, because the body has got a vorticity in the boundary layer. They produce a non-zero contribution. So in general, circulation surrounding a solid geometry is non-zero. It's not 0. So here is a picture of it. Flow over a aerofoil. It's a water tunnel visualization. You have a very, very thin boundary layer on the lower surface, so we can barely see rotating particles. On the upper side, the flow has separated or stalled, so you see a lot of vorticity. So now if you do a line integral around this contour, you're going to get a non-zero value because the vorticity is non-zero. So in general, around surrounding bodies, you'll get some circulation. And later on, we will show that this circulation is related to lift production. In the case of a symmetric aerofoil with the zero angle of attack, what would happen is on the upper surface, you'll have clockwise vorticity, lower surface, you'll have counterclockwise vorticity, and they will cancel with each other when you integrate it. Therefore, you'll get a zero circulation in the very special case where you have a symmetric body at zero orientation or zero angle of attack relative to the free stream velocity. Okay. Now we want to solve the Laplace's equation. We notice that it's a linear equation. So if you have two solutions, phi1 and phi2, if you add them together, there will also be a solution to the Laplace's equation. That means we can add as many simple solutions, which we call building blocks, and then come up with a more complex situation. It's like a Lego puzzle where we take several Lego pieces. Each one doesn't make sense by itself. But when you snap it together, something meaningful emerges. By the way, we can also multiply phi1 by capital constant A, phi2 by constant B. Constants will come out of the expression here. Then you'll get still Laplace's equation would be satisfied. And we do need to, of course, make sure we satisfy the conditions of the aerofoil surface. The body is a streamline, aerofoil is a surface is a streamline. Flow must be tangent to it. That means there could be no normal velocity, normal to the body. So we need to satisfy this boundary condition. The very first building block that we build, or a Lego piece that we look at, is called a simple source in 2 dimensions. Later on, we are going to do 3-dimensional sources, 3-dimensional sinks, 3-dimensional everything in a later video. So this is, since it's 2-dimensional, it's in the XY planes. So this is like a sprinkler. When you turn on the sprinkler, it radiates or shoots out velocity equally in all the directions. There's no preferred direction. So now let's surround it by a round circle. Circumference is 2 pi r. The depth per unit depth is 1. 2 pi r times 1 is the area. The radial velocity is VR, V sub r. So V sub r times 2 pi r times 1 is the volume flow rate of the source. So we're going to call that volume flow rate equal to Q. If Q is positive, it's a source. If Q is negative, it's a sink. In a sink, all the streamlines will flow towards the sink and disappear at the center into the void. So Q, which is the source strength, is circumference, which is 2 pi r, times unit depth perpendicular plane of the paper, so this is the area, times the radial velocity. It's uniform in all the directions, so nothing is changing. So VR is a constant as far as the theta direction goes. It does vary with r. So if you solve for VR, you get this dependency for r direction. So once you have the radial definition for the radial component velocity, by the way, there's no tangential component velocity. V theta is 0. There's nothing is pointing in the azimuthal direction or in the swirling direction. That means if you take a circulation around this contour, ds is pointing this way, v is pointing this way, so they are perpendicular to each other. So circulation around a source or a sink is 0. Now, once you have VR that we found, this is the definition of VR in terms of velocity potential phi or in terms of stream function psi. We can easily integrate it. You will get this expression plus possibly a constant, plus possibly a constant. You cannot pick up a function of theta here, because if there's a plus a function of theta, then d phi theta will become non-zero, then v theta will be non-zero. we saw in the previous slide there is no azimuthal direction velocity at all. Same way, here you cannot have a function of r added to it, even though it will still satisfy this relationship, because the function of r will produce a non-zero v theta. Therefore, this is the solution of phi and psi plus a arbitrary constant that we could choose to satisfy the boundary condition, as we will see later. Now, these lines are velocity potential, radial lines are the streamlines. Remember, velocity is tangent to the streamline. By our definition, velocity potential should be perpendicular to the streamlines. Therefore, these circles are the velocity potential lines. We notice that phi is constant when r is a constant along a circle. We notice that psi is a constant when theta is a constant. Therefore, this is a streamline. These circumferential circles are the velocity potential lines for sources and sinks, both. Now we do the second building block, second Lego piece. This is a uniform flow in the x and y direction. It's a 2D problem currently. So you'll have two components of velocity. Free stream may have in the x direction, it may have a component of velocity called u infinity. In the y direction, it may have a velocity component called v infinity, with lowercase v infinity. So you can define the velocity potential in this manner, because if you take a derivative, you'll get the x component and y component. Or you can define the stream function this way. Then if you take a y derivative, you'll get u infinity. You'll take a negative of x derivative, you'll get v infinity. So this is the second Lego piece. This is for the uniform flow. Again, if we take a contour integral, we could show that because this has got no vorticity, any contour around it will go to 0. There's no circulation in this particular flow. Now I'm going to snap the two pieces together. We only have two Lego pieces so far. So the first one is the source or sink. The second one is the free stream. And the source or sink is currently placed at the origin, which is x equal to 0, y equal to 0. Therefore, r is measured from the origin in this case. This is the building block for source or sink. This is the building block for source or sink. This is the building block for free stream velocity. This is the building block for free stream velocity. Now we can plot contours of these using a Matlab and a very simple Matlab program. So I'm going to show you what happens. Obviously, we have to give some numerical values for u infinity, v infinity, and q, and then solve for the contour plot. So this is the Matlab code we are going to use. I'm going to walk you through this. So basically, we have a huge graph paper where x goes from -1 to +1 in steps of 0.1. So we're going from x equal to -1 into x equal to +1. Every 0.1, there is a graph line, vertical graph line. So we have 21 lines going from left to right in a vertical direction. We also define y the same way we define x, -1 to +1 in steps of 0.1. So we have created a graph paper. Now x and y are one-dimensional functions because they're defined only as a one-dimensional array. So if you want to develop what is the x and y at any point in it, at any cross-section of two lines, you can use this function called mesh grid. So it's the intersection of x equal to constant line and y equal to constant line is an xy point. So this is the x coordinate and y coordinate of every point in here. So we have basically created, in this case, a 21 by 21 array of x, 21 by 21 array of y. Now, q is 1. We are going to assume our source is 1. Let's take this 1. We are going to assume free stream is parallel to the x-axis. It's got a unit magnitude. There's no vertical component of velocity. Now, this is the stream function, q over 2 pi. This is pi. Theta is tan inverse of y over x. Remember, x is r cosine theta, y is r sine theta. Therefore, y divided by x would be tangent of theta, tan theta. So arctan of tan theta would be theta. Why do we use a tan 2? Because it will allow the answer to go from plus pi to minus pi. And this is the free stream. This is the free stream. Now we have added all of these things together. So this is the stream function that we defined in this slide here. Q over 2 pi times theta, u infinity y, v infinity x. Q over 2 pi times theta, u infinity y, v infinity x. Then if you ask Matlab, they have a built-in function called contour. I want 20 contour. Then you'll roughly get a contour that looks like this. These lines are the streamlines. These are the streamlines. As they approach the origin, they will move away from there because the source here is generating flow that's pushing the streamlines away from it. In fact, right here, the source is generating velocity in this direction. Free stream is pushing the velocity in this direction. When they match, you get a zero velocity, or so-called stagnation point at the nose. So you'll get a highest pressure here, zero velocity. On either side, the velocity will slowly increase, eventually become free stream. Slowly increase, eventually become free stream. You get a flow over a body. So we have taken two Lego pieces and computed the flow over a nose of a body. This blue line is not coming out of Matlab. It's just my representation of the envelope of the contour. Okay, that's what it is. So this body was defined by Rankine as Rankine's half body. It's the same Rankine we see in Rankine cycle, thermodynamics, degree Rankine. He has developed a propeller theory, a turbine theory, you name it. He's a very versatile person. Now, let's go to put a source here. So it produces a Rankine half body. Let's put a sink here. Okay, so put the one at minus 0.3, other one at plus 0.3. Then you'll have two solutions. Okay, one is due to the source would be plus q times tan theta of y. Origin is x minus 0.3 for the sink, x plus 0.3 minus 0.3 for the source, plus 0.3 for the sink. So you would not just use x, you would use x minus 0.3 or x plus 0.3 for the sources or sinks. Then when you do that, source produces mass, sinks consumes it. So eventually you'll get a closed body, like an oval-shaped body. Then you'll still get the streamlines that go out this way. Again, the source near plus 0.3 will push the flow out this way. Free stream is coming this way. When they equal in opposite magnitude, you'll get zero velocity. So there's a stagnation point. Here the sink is pulling the particles towards it. Free stream is pushing the particle in this direction. When they match each other, you'll get another stagnation point. So you get a symmetric flow. Front and back looks very symmetric. Up and down look very symmetric. Again, you don't get any lift. You don't get any drag. So in the potential flow, in this case, you don't get any lift or drag. But D'Alembert said, wait a minute, if I put an oval-shaped body in the air, I will get a drag. So this is a paradox, D'Alembert's paradox. But in reality, you have a boundary layer that causes skin friction, causing drag. You get a separated flow in the back end of it, like a flow over a bluff body, like behind your car, for example, or a cylinder. Therefore, you get in general lower pressures here compared to the front, so you also get a pressure drag. So if you ignore viscous effects, it's a pure inviscid irrotational flow. In this case, we get zero lift and also zero drag. So let's stop this video at this point, and we'll continue with our